Exercise 5.3, B. Continuing with our work with trigonometric equations and solving them. Today we're going to have multiple trig functions in our equations, which we are going to need to make some identity substitutions in order to rewrite them all in terms of one trig function. We're also going to come across equations where we have period changes that we're going to have to take into account for our solutions. So here, 2 sine squared x plus 3 cosine x minus 3 equals 0. We have two different trig functions. Remember, the function really represents a variable. So in this case, it's like having two different variables in our equation which we are trying to solve. We need to either rewrite this all in terms of sine or cosine. Well, from our Pythagorean identities, we know that we can turn sine squareds into cosine squareds. Sine squared is the same thing as 1 minus cosine squared. Now we have an equation written in terms of just cosine. Distribute that through and simplify. We get 2 minus 2 cosine squared plus 3 cosine minus 3. Collect like terms. As we collect like terms, I'm also going to multiply everything by -1 here, so our leading term, our squared term, is positive. That's how we're used to seeing things when we factor. So we're going to have 2 cosine squared minus 3 cosine x. We have 2 minus 3, which is -1. And since I'm multiplying everything by -1, it becomes +1. From here, factor this equation. This equation is going to factor. It's 2 cosine x minus 1 times cosine x minus 1. Once it's factored, set each factor equal to 0. 2 cosine x minus 1 equals 0. Cosine x minus 1 equals 0. Solve each one of those factors. We get cosine x equals 1/2. And cosine x equals 1. From here now, we need to go to our reference angles. Where is cosine positive? All students take calculus. Tells us that cosine is positive in quadrants 1 and 4. Cosine we know is adjacent over hypotenuse. Opposite side is going to be -√3. So our reference angle in each case is going to be pi/3. From the second one, cosine x equals 1. So let's go back and get these two solutions here. X is going to equal our first rotation is pi/3. Second rotation, all the way around here, is 5 pi/3. Second factor, cosine x equals 1. Sine cosine equals 1, -1, or 0. That's always quadrantal angles. Quadrantal angle that has a cosine value of 1. Cosine is the x-coordinate, do not forget. So that's at 1, 0. And that rotation, notice we're finding solutions between 0 and 2 pi. 0 is included, 2 pi isn't, so we need to call that angle 0 radians, not 2 pi. If you call that 2 pi, it will be incorrect because our solution set is only between 0, with 0 included, up to 2 pi, but not including 2 pi. So our three solutions are pi/3, 5 pi/3, and 0. Second equation, cosine x plus 1 equals sine squared. Two different trig functions. We cannot turn cosines into sines. We cannot turn sines into cosines. The relationship that exists between sine and cosine is only when they are squared. So that's going to be our first step here. The only way I can interchange cosines and sines are if it's cosine squareds and sine squareds. So the first thing I'm going to do right off the bat here is I'm going to square both sides of this equation. On the left, that becomes a FOIL. We get cosine squared plus 2 cosine plus 1. On the right, we get sine squared. Substituting here. We can change cosine squares into sine squares, and we can change sine squares into cosine squares. Which ones do we want to do? Well, we don't want to change the cosine squareds into sine squareds because we still have this middle term then that would be written in terms of cosine. So I'm going to leave the left side alone. The right side then I'm going to change the sine squareds into 1 minus cosine squareds. Now our entire equation is written in terms of cosine. Get everything on one side set equal to 0. We get 2 cosine squared plus 2 cosine x. Subtract the 1 over. Drops out. We're left with that. Factor. We can take a 2 cosine out of everything, which is going to leave us with cosine x plus 1. Set each of those factors equal to 0. 2 cosine equals 0. Cosine x plus 1 equals 0. Continue solving each of those. We end up with cosine equals 0 and cosine equals negative 1. Dealing with quadrantal angles for both of these factors. First one, cosine is 0. Quadrantal angles, x-coordinate correlates to our cosine value. So where is cosine equal to 0? That happens right here at 0, 1. And down here at 0, negative 1. Second factor, where is cosine equal to negative 1 at? That happens over here at negative 1, 0. So our three solutions appear to be at pi over 2, pi, and 3 pi over 2. However, remember, when we square things in an equation, we are introducing the possibility of adding solutions into our equation that may be extraneous. So we need to check these solutions to see if we have created any extraneous solutions here. When we do that, put in pi over 2. Plug back into your original equation. Cosine of pi over 2. Cosine of pi over 2 is equal to 0. So on this side, we have 0 plus 1. On the other side, the sine of pi over 2 is 1. So that's a good solution. Pi. Cosine of pi is negative 1 plus 1. Sine of pi is 0. Negative 1 plus 1 does equal 0. That's a good solution. 3 pi over 2. Cosine of 3 pi over 2 is 0 plus 1. Sine of 3 pi over 2 is negative 1. 1 does not equal negative 1, so we need to throw that solution out. And our only two solutions are pi over 2 and pi. Number 8. This time we have a period change. Remember back to when we were graphing trigonometric functions, the coefficient on the angle part controlled the period. Remember, the period controls then how quickly or how slowly the function starts repeating itself. In this case, we are going to ignore that until the very end. So we're going to solve this as if this were the equation 2 cosine t minus 1 equals 0. So we still want to get the trig function all by itself. Cosine of 3t equals 1/2. Once we have the trig function by itself, we're going to do exactly the same thing that we have been doing. We're going to draw a reference triangle. Cosine is positive. All students take calculus in quadrants 1 and 4. Cosine is adjacent over hypotenuse. Opposite sides, root 3 and negative root 3. Reference angle is pi over 3. So our two rotations here are going to be pi over 3 and 5 pi over 3. Remember on all of the previous ones, when we have found that rotation, we've been done. This rotation was pi over 3 and 5 pi over 3. That was it. X equals each of those. That is because in this one, our variable was x. That is what we are solving for. So in this case, we didn't just find t, we found what 3t is equal to. So 3t equals pi over 3, and 3t equals 5 pi over 3. So now we have not quite finished. We need to finish solving each of these equations now for t by dividing by 3. We get t equals pi over 9, and we get t equals 5 pi over 9. Those are our two initial solutions. This tells us that we need to find all solutions between 0 and 2 pi. Because this function had a period change here, there are more solutions than just those two in between 0 and 2 pi. That coefficient of 3 made our period smaller, therefore it's going to repeat more often, and in this case has more solutions now between 0 and 2 pi. We know our standard period for a cosine function is 2 pi. We found our period when we were graphing by taking 2 pi over the lead coefficient. So there now is the period of this cosine function. So I need to take each one of these two solutions and I need to keep adding that period to it until I get a value larger than 2 pi because we're only finding solutions between 0 and 2 pi. Remember, 2 pi over 3 with a denominator of 9 is the same as 6 pi over 9. So I'm going to take that, I'm going to continually add that to pi over 9 until I get a value larger than 2 pi. So our solutions are pi over 9, 7 pi over 9, 13 pi over 9. If I add it again, I get 19 pi over 9, which is bigger than 2 pi, so I know I'm done there. Take your second solution of 5 pi over 9. Add the period. Add 6 pi over 9 to that. We get 11 pi over 9. Add 6 pi again. We get 17 pi over 9. If I were to add it again, I get something larger than 2 pi. So those are the 6 solutions between 0 and 2 pi. Remember, we talked in section 5.3a about the general solution. Our general solution here would look like pi over 9 plus the period, which remember the period yesterday was always 2 pi because there were no period changes, times n, and 5 pi over 9 plus 2 pi over 3 times n. That would be the two general solutions. If you were asked for that, you weren't in this case. You were asked for these 6 solutions because those are the only 6 of those general ones that are between 0 and 2 pi. Number 9, solve for tangent of x over 2. So we can see right away we have a period change here, but we're going to ignore that until the end. Tangent of x over 2 equals, subtract the 3 over, divide by 3, we get negative 1. So we're drawing reference triangles where tangent is equal to negative 1. All students take calculus, tells us that tangent is negative in 2 and 4. Tangent is opposite over adjacent. Should recognize this triangle as being a 45, 45, 90, which means these reference angles are pi over 4. So we have this rotation, which is 3 pi over 4, and that rotation, which is 7 pi over 4. Because of this period change, we just solved for this angle right here. So that means that x over 2 equals 3 pi over 4, and x over 2 equals 7 pi over 4. Solve for x, we get x to be 3 pi over 2, and we get x to be 7 pi over 2. By adding that fraction in front, because that fraction is less than 1, we've actually lengthened the period. So we've lengthened the time that it's going to take for this function to start repeating itself. We are only finding the solutions between 0 and 2 pi. The only solution between 0 and 2 pi is that one right there. This is 3.5 pi or 7/2 pi, so we do not need to list that solution. The only solution between 0 and 2 pi is 3 pi over 2. Remember, for a tangent function, if this comes up in the homework, normal period of a tangent function is only pi radians. So this one has a period of 2 pi radians. We didn't need to do that here because we were only finding between 0 and 2 pi, but that is how you would identify the period, don't forget, for a tangent or cotangent function. Last one. Secant squared minus 2 tangent x equals 4. A couple things we're going to need to do here. First of all, we have an identity that we need to substitute in, so we can rewrite all of this in terms of tangent. Secant squared we know is equal to tangent squared plus 1. We're going to subtract the 4 over in that same step. Simplify this equation. We end up with tangent squared minus 2 tangent minus 3 equals 0. Factor tangent x minus 3 times tangent x plus 1. Set each of these factors equal to 0. Tangent x equals 3. Tangent x equals negative 1. Reference triangles for each of these. First one, tangent is positive. Which quadrant is tangent positive in? 1 and 3. Tangent is opposite over adjacent. That's not a triangle you know. It's not our 30, 60, 90 triangle. It's not our 45, 45, 90 triangle, but we can use the calculator to find those solutions. Let's go over to the second one first. Tangent is negative 1. What quadrants is tangent negative in? 2 and 4. Tangent is opposite over adjacent, opposite over adjacent. This triangle you should recognize each of these reference angles as pi over 4. So our two solutions from here are going to be 3 pi over 4 and 7 pi over 4. Going back to this one, that's not a triangle that you recognize. It does not mean that there is no solution. It just means it's not one of the two that we have memorized. So we need to go to the calculator and we need to find what the reference angle is going to be. So in our calculator here, make sure you are in the correct mode. We want radian measures here, so make sure you are in radian mode on your calculator. We want to know what angle has a tangent value of 3, so we're going to go second function tangent or inverse tangent of 3, hit enter, 1.249. So using that and going back to this, 1.249 is this reference angle and this reference angle. Remember, the reference angles are always the same in both triangles. So our two solutions that we are going to get, well, this first rotation is 1.249 radians. Our second rotation now goes to there. We know if we go halfway around, we've gone pi. We go 1.249 radians past pi, so take pi plus 1.249, and we get 4.391 radians. And there are our two solutions. Or I'm sorry, our four solutions. To each one of these, if we add pi to it,